Good morning everybody. Welcome back to our third session on basic electronics. As you are aware, we were already discussing about module 4, and in module 4 we have spoken about the first part, that is latches and flip-flops, and once we understood that, we moved on to microcontrollers in our previous session. And just to recall what we discussed in our previous class, in our we basically spoke about what is a microprocessor and then what is a microcontroller, and then we discussed the differences between the two. So just to recall, you can see a microprocessor is the main unit will have only the central processing unit. I told you, please remember, CPU is something which does all arithmetic and logical functions, and it stores the results of those operations in different registers. One of them is the A register or the accumulator. The control unit, where all the controls, how the signals should move, how data should move, and how the address should be sent, all kinds of control, when serial data should come in, when printing data should go out, all kinds of controls are managed by this, and both these lie on the same chip, that is the central processing unit and the control unit. But other than that, any other external interfaces like the input module, the output module, and the memories, basically program memory or code memory and data memory, all of them will lie outside the main device or the main IC. So this is a microprocessor. So we discussed it is a general purpose usable board, and any general purpose program or application can be implemented on a microprocessor. And we've already spoken about the various examples. Today our laptops, all our desktops, PDAs, everything, mobiles, they all have microprocessors. Whereas coming to a microcontroller, the architecture of a microcontroller is such that all these blocks, that is the internal and external memories, that is this ROM, RAM, and then the IO ports to take in inputs and outputs, the serial communication bit, and the timers for generating timing delays or generating waveforms, counting events, so on, and the interrupts. So when some process is running, you can always interrupt, and suddenly some data comes in through the serial port, you can always send an interrupt to the present executing program and say there is a urgent data to be taken in. Then the processor will stop its work adhering to the interrupt. It will come and take in the data, store it in some location, and then once the interrupt is heeded, it will go back and continue its previous work. So all these things we have discussed. And bus control. So we were discussing in detail about the different features of 8051, and in that the first thing what we considered were the A and B CPU registers. We call them as CPU registers because they are mainly used with all CPU operations. I told you yesterday to remember that one of the operands is always stored in the A register usually, and wherever there is a multiply or divide function, then the other operand will be stored in the B register. So usually the result of operations will also be present in these registers. So I hope all of you remember what is a register. Basically, I told you a register is nothing but it is a sequence of flip-flops interconnected or in line, in parallel. So each one is a flip-flop. So flip-flop 1, flip-flop 2, 3, so on. So we have a set of flip-flops put together to form a register. This is called as a register, and this register will be either 4-bit in length or 8 bits, and in our microcontroller 8051, almost all the registers are of 8 bits length. Every register will be of 8-bit length in our current microcontroller. So please remember, a register is nothing but a collection of flip-flops where data can be stored in parallelly or serially. So if I call it a shift register, then I can shift in data from one side. So if I shift 1 to this, say for example I shift 1 to this, initially it had a 0, this 0 will go and sit in the next, and whatever was there in this, that will go to the next. It is a shift register in that case. So then we can serially send in data. Otherwise, we can parallelly load data into all the flip-flops simultaneously. Whatever data we have, 8-bit data could be stored parallelly into each and every flip-flop, and this is what is a register. So this is what you studied. And coming to the next registers, they are 16-bit in length, and they are nothing but the program counter and data pointer. And program counter is nothing but it is a pointer which points to where we have saved or stored our program. So you have stored your program in code memory or program memory, and this data pointer is a 16-bit address, or it contains a 16-bit address which always stores the value of the next instruction that is to be fetched. So whatever is the next instruction which has to be fetched, that address will always be there in the program counter, and this data pointer will always have a 16-bit address for the data which has to be brought into the controller. So program counter and data pointer are both 16-bit values. They store 16-bit addresses. Program counter stores the address of the next instruction which has to be fetched from the program or program memory, and data pointer will have the address of the data which has to be fetched from the data memory. The next one what we need to discuss is an 8-bit word, also known as the program status word. So 8-bit registers we call as 8-bit words here. So what is this program status word, or PSW in short? This program status word has multiple bits. It is bit accessible. Yeah, this is bit accessible, as you can see, and there are 8 bits in total, of which the first one is called as carry bit. What happens when is this carry flag? We also call them as flags or bits. So when is this carry flag set? This carry flag will be 1 if the result of addition or subtraction will generate a overflow out of the 8th bit. So you add two 8-bit numbers. Take for example, I have something like this, 11111111. When I add two such numbers, naturally the addition of the MSB, this is the most significant bit. When I add these two, it will result in 10, which means I already have 8 bits here. So 8 bits are already done by adding these two, this plus this. There is a overflow out of the 8th bit, and this we call as the carry flag. So this is known as the carry flag. So if there is a 1 generated out of this bit, then the carry flag is set. So normally it is during addition, but this can happen during subtraction also. So we can have the same thing during subtraction also, or a borrow can be generated normally. So carry can be result of addition or result of subtraction. Result of addition or subtraction if there is a overflow after adding two 8-bit numbers. Out of the 8th bit, if there is something, or a carry or borrow is generated, then the carry flag will be set. Okay. So this is about carry. The next one is called the auxiliary carry flag. What happens in this auxiliary carry flag? This auxiliary carry flag is generally the result of addition after the 4th bit. So, you add two 8-bit numbers just like how we had before. Any two 8-bit numbers can be considered. So, out of 4 bits, so I will just take the lower 4 bits. This is the LSB, least significant bit, and I have the MSB. It is just a nibble or 4-bit numbers, two 4-bit numbers. When I am adding two such 4-bit numbers and when I add the 4th bits of both, it results in a value out of the 4th bit. So, this value is nothing but the auxiliary carry. So, auxiliary carry flag will be set if at all there is a flow out of the 4th bit whenever we add two 4-bit numbers. So, generally we use this principle in adding BCD numbers. I hope you all remember what is BCD, binary coded decimal. So, when we add two BCD numbers, we always need to take into account 4 bits at a time or one nibble at a time. So, this is the working of auxiliary carry flag. And next is this F0. F0 is an unused bit. It is available for general purpose. As it is written here, there is no definition given for F0. Usually when they design such devices, they would leave 1 or 2 bits blank so that some usage could be defined further by the people using them, and if required you can set it to something, otherwise it is an unused bit for as of now. The next two bits here are RS1 and RS0. They are, RS stands for register select. So, we have two bits for selecting one of the 4 register banks. You can see here the table is given below. If RS1 and RS0 are both zeros, then register bank 0 is selected, and register bank 0, if you remember, I told you every register bank will have 8 bytes of data or 8 words. So, the address for those 8 bytes, it will start with 00 and it will go up to 07. So, you have 8 counts. Similarly, 01 selects register bank 1, the address begins from the next number 08 to 0F, the next 8 bytes. Similarly, 2, register bank 2 has address from 10 to 17. Remember, all these addresses are always written in hexadecimal. We use the hexadecimal numbering system to represent the addresses because it is a 16-bit value and it is easy. Even if it is 8-bit, we always write it in hexadecimal. So, 10 here represents 16th memory location in decimal system. 10 stands for 16, so on. Now, the last one is 11. When both the register select inputs are high, it will select register bank 3 and the address for this will be from 18 in hex, H here represents hex, to 1F in hex. So, totally 4 register banks could be addressed or selected by having 2 bits which are register select bits in the program status word register. So, you can use this PSW register and you can choose the values of these 2 bits RS1 and RS0 and choose one out of 4 register banks. So, next comes, so all these registers, the storage present in register banks are for general purpose storage. You can store the result of some arithmetic or logical operation, you can store data, you can store anything. It is for general purpose. The next flag here is the overflow flag. This overflow flag, as the name indicates, is used with signed numbers. Only when we are working with signed numbers, we are going to make use of overflow flag. So, what are signed numbers then? Signed numbers are those where MSB bit represents the sign of the number. So, in a 8-bit word, in 8-bit, only 7 bits will give you the value and MSB bit will always represent the sign. The remaining 7 bits will give you the value of the number, the data, but the 8th bit or the MSB bit is the sign bit. If the sign bit is 1, it is a negative number. If the sign bit is 0, it is a positive number. So, what are signed numbers? Signed numbers are nothing but 8-bit numbers only, where only 7 bits are used to store the actual value, or they mean the actual value of the number, and the 8th bit gives us the sign, whether it is a positive number 0, for a negative number it would be 1. So, in signed addition or signed multiplication, whatever, whenever we are doing operation with signed numbers, if there is an overflow out of the 7th bit, so if we have, as I told you, you have an 8-bit number, so 10, 11, 11, 10, whatever, and this is something like this. When we perform any operation, so we are going to consider only till 7 bits. This will represent the sign bit and you should not consider this 8th bit. So, here 0 plus 1 is a 1 and there is nothing coming extra from here. That means the overflow flag will have a value 0. Supposing I take this number as value as 1, then 1 plus 1 what happens? 1 plus 1 is 1 0 and I will have a 1 carried over to the next bit position. Then this overflow flag will be set. It changes to 1. So, please remember, overflow flag is similar to the carry flag or the auxiliary carry flag. Carry flag operates after the 8th bit. It operates for unsigned numbers, whereas overflow flag operates for signed numbers. So, this is about overflow flag. And then the last one here is the parity flag. This parity flag talks about, it helps us in some kind of error detection or some security added to the data. So, if this parity flag is set, then that means there are even odd number of ones in the data. So, it depends on how many ones are present in the given data. Normally, this will monitor the contents of the A register, accumulator or A register. So, it will be set for odd number of ones, it will be reset for even number. So, this is about the parity flag. Next, so this is the complete program status word register and how we can use this in our programming. So, if I have to check the result of different operations, I can always make use of this PSW, and if you want to select one out of the 4 register banks, one data there, you can always use this. And the next one what we need to study is the 8-bit stack pointer. So, what is this stack first? Stack, as the name indicates, just like how we say in hotels, you see how they stack plates one on top of the other. You will see once it goes for a wash, it is simply stacked one on top of the other and a long stack of plates will be formed. So, similar to that, here stack in our microcontroller refers to one particular area of the memory. So, as you can see here, this stack you can see is mentioned here, register bank 1. So, it starts from here, this is where the stack starts, register bank 0 will not be used. You can start the stack from here, generally register bank 1 would be sufficient. If you have more data, you can extend this to the other register banks. It can go to register bank 2, register bank 3, so on. So the stack starting location address is 7. So after the first 8 bytes, the first 8 bytes represent register bank 0. Just after that you have register bank 1. This register bank 1 starting position is the beginning of the stack. So this stack is just a special area in the memory which helps us in using or putting data, taking out data. You have some instructions which specifically use the stack. For example, this program status word which we discussed before, there is an instruction which will send the contents of the program status word only onto the stack. You can't take it out anywhere else. You can't read the program status word anywhere else. Remember, we are using a RISC processor, reduced instruction set processor. So number of instructions are minimum. With those minimum instructions, you should be able to do all the operations. As I was telling you, one instruction in that will push the contents of the program status word on the stack. So I have to take out the data from the stack to read it. We will see what are these push and pop operations. So how to work with push and pop operations we will see. So basically for now you just remember, stack pointer is nothing but it is a specific pointer which points to the beginning of the stack. So wherever the stack starts, it will point there. If something is put on the stack, then it will point to the last entered value on the stack or the last stored value on the stack. This stack is called first in last out or last in first out memory. LIFO we call it as. So whatever goes in last should be brought out first. Just remember, it's exactly like those stack of plates, one on top of the other. So if you try to take the lowest one, you had put the lowest one first, but if you try to pull it out, you will not be able to pull out the lowest one. All the others on top will fall off. So it's always better to take what you put in last, you should be able to take out first. It's just like that. You go on putting or stacking data one on top of the other. Whichever data you put in last, the stack pointer will be pointing to that data and you have to take out that data first. Okay. So that's how you have to take out the data. So as I told you, stack pointer is always points to the last stored location or last used location on the stack. We have two kinds of operation which can be performed on the stack. One is the push operation and the other is the pop operation. We will see what is this push operation. So this stack here has the stack pointer is pointing to the location. This is the beginning location 07. That's where the stack starts. So it has some data, let me say 15, 16, EF, whatever. So some data is already there. So if I just use the instruction, so push some value 15 or something like that. I am just taking an example. So you have to, what should you do? The stack pointer, once this is filled, the stack pointer will come and sit here. Stack pointer is an address pointer. It will point to this location. So once there is a push operation, this stack pointer should be decremented. So here what is the next number here? This is 08, 09 and 0A. The next value the stack pointer will take is 0B. So the stack pointer should now point to 0B and then whatever data I have in the push instruction, that data will be entered onto the stack. It will be pushed on the stack. So it is just like pushing a plate onto a set of you already had 3 plates here, 15, 16 EF. On that you are pushing another plate with value 15. So the stack pointer will now point to 0B, the last entered location of the stack. Okay. This is how a push operation is carried out. Now we will see what is a pop operation. Say I have to do pop 15. That means I just have to take out the last entered data. So from the stack, as usual, the stack pointer is pointing to 0b. So what should I do? I will see whatever is saved in this 0b and I will take it out. 15 is taken out from here. So now this becomes empty. There is nothing here. So there is no data, or this data becomes empty once 15 is removed from this location. So what do you do now? You have to readjust this stack pointer to now point to the location 0a, because now this EF is the last filled location. I have this, all these three locations as it is. So now the last filled location would be EF, because 15 has been removed out, popped out. One plate has been taken out. So the address of the pointer should point to the next filled location, that is 0a. Is this clear? This is how a push and pop operation is conducted on the stack. So as I told you, stack operations are very important and they are used normally with respect to any microcontroller or even in a microprocessor. So as it is mentioned here, push operation will first increment the stack pointer and then copy the data onto the stack. Pop operation will first copy the data out of the stack, pop the data out and then decrement the stack pointer. So please remember, as I showed you, in this microcontroller the stack will grow upwards. So from a lower memory to higher memory. You saw the lowest memory address of the stack was 07, then it incremented to 08, 09, 0A, 0B, so on. So this is how the stack works. On power up, as I told you before, stack pointer will point to the lowest location, that is 07. So the default register bank for the stack is register bank 1, but the others, higher banks, register bank 2 and 3 can also be used for the stack area. So that is about stack. Remember, stack is one specific area in memory. Now we will discuss the detailed memory organization in 8051. So all these things we have already discussed in the architecture. There is a 4K internal ROM to store program, 128 bytes internal RAM to store data and operands. Then 4 register banks will be part. Out of these 128 bytes, there are 4 register banks, each of them having 8 registers. So 8 4s, 32 registers in total out of 4 register banks. Then 16 bytes which may be addressed at the bit level. So we have 16 bit addressable memories. Every bit can be addressed. It would be very useful for us if you could address each and every bit of a word. You have an 8-bit word, I have to address only the second bit. I want to make some change only in the second. So if you could address that separately, it would be very useful. That's what is available there. And finally 80 bytes of total general purpose data memory. So as I've mentioned before, 8051 follows Harvard architecture. Harvard architecture means separate memories for program and data storage. So programs or code will be stored in a separate memory area, data will be stored in a separate memory area. Please remember that. So internal memory, as I've told you many times before, 4 KB ROM, 128 bytes RAM. I hope all of you remember what is ROM. ROM is read-only memory where you can only write into it once and usually it is stored permanently, not erasable. So today we have erasable ROMs, but ROM means permanent storage. RAM means random access memory. If you write once, the next data you write on top of it, it will be overwritten. The older one will get erased. So that is RAM. External memory can be connected up to 64 kilobytes of both data as well as code memory. So both program and data memory can be extended up to 64 kilobytes as it is shown in this diagram. So external memory can be added. You already have some internal memory. You have two special pins. One is the program store enable pin, PSEN it is called. We will discuss a little bit after this. And the other is the external access, EA. So both are active low. As you can see, it is EA bar and PSEN bar. So program store enable and external access, both these pins will help us select either an internal or external memory and access those correctly. So this is ROM, read only memory, and this is RAM, data memory, read write memory we call it as. You have from 00 to FF, FF stands for 2 power 8 or 256 bytes. So totally we have 256 bytes of internal storage, out of which it is divided into two portions of 128 bytes each, and how this division takes place we will see in the next slides. So the same thing what I explained, code memory is accessed via the program store enable pin and the external access pin, EA bar we have, and data memory we normally use read write operations. For code memory it is read only, we can read the data, you can't write into it, writing is only once, whereas for this data memory you can do both read and write operations. This is on chip memory, this is external memory. You can see the address here, all zeros to all F's, that means it is totally 2 to the power of 16 or 64 kilobytes. Okay. So I talked about two important pins which will be useful in memory selection. One is the EA bar or the external access, and especially in case of lower versions of 8051, that is 8031 and 8032 are lower versions of our current 8051 microcontroller. In these versions, this EA bar pin is always connected to ground to indicate that code is stored externally. There is no on-chip memory in that 8031. So you should always have external memory where the program or code will be saved. So it should always be connected to ground. This program store enable pin, active low, you can see this bar indicates active low. The pin numbers are also mentioned. It's an output pin which is connected to the output enable pin of the ROM. So every device will have an enable pin. To enable that device, you should be able to give the correct signal on the enable pin. So if you connect the correct signal on the enable pin, that particular device will be enabled to work as it is required. So each and every device should be enabled separately, and this PSEN is used to enable the external ROM. Other than this, we have another important pin, the address latch enable or ALE. What's the meaning of this address latch enable? It is also an output pin, pin 30, it is an active high pin. So I think I have it in this picture, you can see here. So what is happening in this picture? Okay, so this is the 8051 controller and this is the external memory EEPROM which is connected. This port 0 in 8051 will initially carry the lower byte of address. So the lower 8 bits of address, say A0 to A7. Remember, address is 16 bits long and the lower byte of address will be carried on port 0 of the microcontroller initially, and later on the same 8 bits, this bus as we are talking, a bus is a collection of data wires to carry data, it is just a collection of wires. So this is an 8-bit bus. So the same 8 bits will be carrying data in the next clock session. maybe during the first clock cycle these 8 bits should carry the address. So, P0 should have address during the first clock cycle, and during the second clock cycle the same value should have data. So, the same 8 bits are going to carry data during the second clock cycle. So, then what happens to the address? That address should be available even during second clock cycle. If I overwrite it with data, then address will be lost. So, what do we do? Whenever address is available on this, that address will be stored on latches. We all know latch is storage devices. I will use an 8-bit latch here to store the 8-bit lower byte of the address, and from here the lower byte of the address A0 to A7 is continuously available. The higher byte of the address A8 to A15 is available from port 2. So, from port 0 I have A0 to A7, and from port 2 I have A8 to A15. So, totally the combined 16-bit address is available to address any location in the ROM. So, remember ROM has 64 kilobytes totally. So, I need 16 bits to address one out of the 64 kilobyte location, and in order to do this, this address latch enable pin what we have, this pin should be made active high. Whenever I make the address latch enable pin high, so this pin, whatever address is available here, that address will be saved on the latch, and once it is saved on the latch, it is available for further usage here. So, totally 16-bit address will be available, and ALE stands for address latch enable. It is made active high to store that data. So, this is how, what are we doing here? Why are we using the same port 0 8 pins to carry address for some time and then data for some time? Remember, we are saving on the area the number of pins needed, and only the timing will vary. During one clock cycle I send the address, then I save that address on some latches using the ALE pin. The ALE pin is to enable the latch to store the address which is present on port 0. Now, the port 0 is free to carry the data in the next clock cycle. So, this is how ALE works, and here also we can see in the second diagram we are trying to access data from data memory, and the EA bar pin is connected to VCC. So, active low pin it is connected to VCC because we are accessing data from the data memory. Here also ALE is there to enable the latch. Port 0 when it carries address it saves it on the latch, and then port 2 when it is carrying address it will be available here. So, how many bits of address I need? That many bits I am going to use. Read and write bars of 8051 are connected to read enable and write enable pins. So, this is how we do the memory accessing. The other pin which we should know of 8051 is the reset pin. So, as the name indicates, it is an input pin and it is active high. It is normally a power on reset. That means, if at all we give a high value to this reset pin, the microcontroller will reset and all the values in the registers will be lost. That means, I will give you an example here. You can see the contents of the registers. So, the program counter, PC stands for program counter. Once the reset is given, it will point to 0000, accumulator, the A register, it will also be 0, B register becomes 0, program status word becomes 0, stack pointer will point to the initial location of the stack, beginning of register bank 1, data pointer will contain 0. In RAM, all the values are in the read write memory area, all contents will become 0. So, on reset, most of the registers will be changed to 0. So, please remember this. So, the RAM memory space allocation we have already seen. Register bank 0 will be from 00 to 07, the lower 8 bytes, next 8 bytes by register bank 1, that is where the stack also starts, then register bank 2, register bank 3. So, totally from here to here we have 32 bytes of data. Next, bit addressable RAM we have from 20 to 2F, then the standard general purpose bytes or scratch pad RAM we call it as. So, how it is done specifically we are seeing it here. As highlighted here, the general purpose registers are available from 00 to 1F. So, register bank what? Register banks 0 to register bank 3. Okay. All the 4 register banks are covered in this first block. The next block of 16 bytes is bit addressable memory, and the remaining values will be used for different purposes. We store special function registers there. So, as you can see, it is divided, total 256 bytes is divided into lower 128 and upper 128. The upper 128 is normally used or shared with special function registers. So, upper 128 and special function registers will share the same area. So, totally it has 384 bytes, and we will see what is this bit addressable. You can see the filled section here. So, the filled section here is nothing but the bit addressable area. So, it is totally 16 bytes. This area occupies 16 bytes. Each and every bit is separately addressable. That means I can get access to every single bit separately from the program. So, from whatever code or program I write, each and every bit could be accessed. These are the 4 register banks. This is the general purpose storage area. So, this is how the lower 128 bytes, this what is marked in red indicates the lower 128 bytes. This is how it is divided. So, next the upper 128 bytes, as I told you, is shared with the SFR or special function register area. There are around 25 well defined special function registers. The remaining are free. You can see this remaining area is kept free. You have the accumulator, the B register, the program status word, the timer control, serial control, interrupt priority, all multiple registers. I told you totally around 25 registers in the special function register area. So, this special function register area is shown again here, and all the special function registers are mentioned on the right hand side. So, basically how do we define these special function registers? These special function registers, as the name indicates, they provide special control and for data exchange between the microcontroller and the peripherals. So, when I need to do some special functions of data exchange, I will be making use of these SFRs or special function registers. To set values in the peripherals also, we use different control registers. Serial control to set the correct control operation for the serial interface. Then interrupt enable. If I want to enable external interrupts, I am going to make this high. So, I have different control registers where I can set each bit separately to do different control operations, especially when the microcontroller is speaking with its peripherals. When it is communicating with its peripherals, you should be able to control how that operation happens. So, that is about the special function registers. Then we have 32 input output pins arranged as 4 8-bit ports, port 0 to port 3. What is the use of each of these ports? Let us see. So, port 0 to port 3, port 0 has 8 bits, P0.0 to P0.7. It is an 8-bit read-write memory which is used for general purpose, but we have already seen how it is used in memory accessing also. It is used for specially as to carry the lower byte of address for one clock cycle and then the data for the remaining clock cycle only when we interface some external memory to the 8051. So, whenever we interface an external memory, that external memory should be addressed. So, lower byte of address will be carried by the port 0, 8 bits for one clock cycle, then it will carry the data. Port 1 also has 8 pins from 1.0 to 1.7. It is a general purpose input output port. Then we have port 2, 8 pins again. It is also used for general purpose input output, but during a memory access we already saw port 2 would carry the higher byte of the address bus. I need 16 bits in the address. The lower 8 bits will come on port 0, the higher 8 bits will be carried by port 2. Next comes port 3. Port 3 is also used for general purpose input output normal operation, but when we interface peripherals, then some control signals are multiplexed with this. I hope all of you know what is multiplexing. Multiplexing means sending multiple signals over a common line at different instants of time. So, during time 1 I will send address, during time 2 I will send data. Just like that in port 3, during some time it is used for taking an input or sending an output data, but at some other times I will be using it to send some control signals. For control operation we make use of it. So, that is about I/O ports, and all ports are bidirectional. It can work both ways, either input or output. Then we have two 16-bit timers or counters. So, this timers can work in two modes. One is called the timer mode. This timer mode is used to generate waveforms or delays. We can generate different types of waveforms or delays in the timer mode. In the counter mode, I can use this timer to count events. Say some event is happening, how many times it happens? It can be used as a counter just to count the number of times. Then timer 1 can be used to provide programmable baud rate. So, during serial communication, I have to control how data flows, the timing, whether I can send 10 bits per second or 100 bits per second or 1000. This is called as baud rate or bit rate. So, the rate at which data is transferred on the serial communication line. So, that rate will be set by this timer 1, normally whenever serial communication take place. Then this timer and counter operations can be controlled using two control registers. One is called the timer mode control register, T mod it is called. Both these are SFRs, special function registers. So, the timer mode control register is used, and the timer control TCON, both of them will help us in controlling the operation of these timers. Along with that, we have TH0 and TL0, timer high and timer low. Remember, they are 16 bits. So, 16 bits is divided into two parts, high byte, higher value and the lower value, and they store the count. Similarly, just like that is for timer 0, timer 1 can have TH1 and TL1, and in 8052, it is a higher version of 8051, we can have TH2 and TL2. So, basically timer has these values. So, just remember, timer can be used to generate waveforms or it can be used to count events. So, that is about the timer. And can I finish this? Next is the okay. So, the next thing what we have to discuss is about the serial data transmitter and receiver. So, just before winding up, I will just talk about, today we discussed in detail about the program status word register and its functions. Then we discussed about the memory organization in 8051, how much of internal memory, how much of external, what are the different pins which help us in accessing external memory, program store enable and external access pin. And finally, we discussed about special function registers in brief, and also about the timers. So, next class we will continue with this, and we will talk about the remaining features of 8051. So, till then you please get back if you have any queries. Thank you.